All right, so we're going to look at the last part of 11.2, which is on an infinite series. So now the idea is, how can you add up infinitely many numbers and actually get an answer? Well, you can only do that sometimes. Depends on the kind of numbers you're adding. Okay. But before we look at the infinite series, there's one thing that connects with kind of what we did yesterday. I want to expand each of these. Okay, so that's, what's the name of this notation? Sigma. I want to write expanded. So let's expand each one of these out and see what we get. First of all, do they look exactly the same? The way they are on the board? No, they look a little different. But let's see what happens. For the one on the left, what's the first number you would plug in for k? Right. So you're going to plug in a 1, and that's going to generate your first term. What's 3 times 1? 3. Right. What's the next value we plug in for k? 2. 3 times 2? 6. Next value? 3 times 3 is 9. Next value is 4, and 3 times 4. And now we're at the last value because 5 tells me to stop. What's 3 times 5? 15. So when you do the one on the left, I don't care what it adds up to, but that's how you do it. Now let's do the one on the right. To get the first term that we're going to write down, what do you plug in for k? You start with a 2. Right? Let's plug that in. What's 2 minus 1? 1. What's 1 times 3? 3. What number are we going to plug in to get the second term? We're going to plug in 3. What's 3 minus 1? And 2 times 3? 6. The next one we're going to plug in after 3 is 4. Go to 4. 4 minus 1 is 3. 3 times 3 is 9. And you can see what's going to happen. 5 is the next one. That's going to be 4 times 3. And 6 is the last one. 6 minus 1 is 5. 5 times 3 is 15. So how does the answer to the left problem and the right problem compare?
The same.
It is the exact same thing. There is no difference between those two problems. And the reason I'm showing you that is because every problem we did yesterday, we always started with the number 1 to plug that in and to get our first term. But you don't have to start with 1. You could start with 2. I could start with 3. I could write a version of this that starts with 607 and still get the same answer. I just have to adjust it to make it work. So I'm showing you that because you might have a problem that says expand, and it might not always start with a 1 on the bottom. So you have to start with whatever number they give you. Okay. Any question on the difference between those two? Okay. All right. So both of those are what we call finite. They're finite because they stop. You're adding up 5 things, and then you're done. When you have an infinite series, you're going to be adding up an infinite amount of numbers. So first of all, that is not possible to do by hand. You definitely can't add up infinitely many things by hand. And sometimes when you add up infinitely many things, it doesn't even add up to something. Right? The answer just gets bigger and bigger. When could it? Well, look at something like this. Let's say we had 20 plus 10 plus 5 plus 5 halves plus 5 fourths. What's happening each time? It's halving, right? It's halving every time. So eventually, if we keep halving the number that we're adding, what is this number getting closer and closer to? It's getting closer to 0, right? So we started out with 20, and we just kept adding half of it each time. Because this number is getting closer and closer to 0, you could add up every number from 20, having it forever, and get an answer. Okay? Because eventually this becomes so small that it really doesn't even make a difference anymore. And if you did add up every number in that list, and you kept going, like forever, it would approach 40. Okay? The sum of all of these added together would get very, very close to 40. It would never reach 40. It would get to like 39.9 repeating. Right? But that's what I want to show you how to figure out. Right? Now, if you had a list like this, what's happening to the number each time in this list? It's doubling. You can't add up every number from 2, doubling it forever to infinity. Because what's going to happen there is it's just going to get bigger and bigger and bigger. Because the number that you're adding is getting bigger and bigger and bigger. So something like this, we can add up all the numbers to infinity. Something like that, you cannot. Any question on the difference between the two? All right, so let's look at that. So this is what I just said to you. So there are some series, in particular, this is one example of what I'm talking about. There are some series that when you add up an infinite amount of terms, you actually can come up with an answer. That top one, again, that would add up to 40. That would add up to 40. Or it would approach 40. So when we add up an infinite amount of things, we can't technically say that it ever reaches the number, but we say that that number is like the limit. It's like an asymptote. So it gets very close to. But one thing we want to be able to determine is when can you add them up and get an answer versus when can you add them up and not get an answer. Right? That's the first thing we have to figure out. And then if it's a problem where you can get an answer, okay, now how do you get it? Okay, so first of all, that's the notation for an infinite summation. What do you notice is different with the part that I just circled from yesterday? Right, there's an infinity symbol at the top. When there's an infinity symbol at the top, that means you never stop. And what do you notice what's different on this side? Something different on the right side that wasn't there yesterday.
Subscripts?
The what?
I might just be like saying by the extra dot dot dot.
The extra dot 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 where?
On the very end.
On the very end, yes. We never had a problem yesterday that had a dot 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 on the end. When you put the dot 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 on the end, it means that it keeps going forever. The ones we did yesterday looked like this. That's finite because it stops. That's infinite. Any question on the notation of what you'll see when I ask you about an infinite? That's what you'll see. And here you'll have a formula. Okay, maybe it'll be like 2k plus 1. Maybe you'll have a formula there. So adding up an infinite amount of numbers by hand, not going to work. So we have to come up with another way to figure out what an infinite amount of numbers would add up to. We cannot directly calculate it. Is there any question why you can't directly add up an infinite amount of things? It would take a long time. You don't have enough time to do it. All right, so we're going to think of it this way. Instead of thinking of adding them all up, the first way we're going to think of it is as a picture. So if there is a number, okay, and for that last problem we talked about, let's say the number is 40. So if there's a number that you can draw a horizontal line at that number, and you graph your sums on the calculator, and as you graph them, it looks like you're getting closer and closer to that number, but never reaching it, then we would say that that number that you're never reaching, but you're getting close to, that is the sum of the problem. Okay, it's a number that's a horizontal asymptote. So you get close to it, but you never reach it. And the word that we use to describe that and say that it's getting close to a number but never reaching it is converges. Converges means you get closer and closer to a number, but you're never reaching it. And I'll show you an example where we draw a picture and take a look at it. Okay, so if you can find a horizontal line that you could put in your graph, and when you do your sums, it looks like you're getting close to that but never reaching it. That horizontal line, whatever number it's at, that's what the numbers would add up to. Okay, so let's look at this one. I want to add up every number from 1 to infinity in this series. Let me type something in. 2/3. So now we'll do a couple by hand, but then I've already done some of these up. So let's start by just adding up like the first term, first 2 terms, and first 3 terms. First thing we need to do is generate the numbers we'd be adding up. What's the first number that we would plug in for k? 1. Okay, so let's make a chart. So this will be the k value and the term. When we plug in 1 for k, what's 1 minus 1? 1/3 to the 0 power? 1 times 2. 2. So the first term in that sequence is a 2. Let's get the second term. So now plug in a 2 for k. What's 2 minus 1? 1. What's 1/3 to the first power? 1/3. And what's 1/3 times 2? 2/3. Let's do 3. So 3 minus 1 gives me 2. What's 1/3 to the second power? 1/9. And what's 1/9 times 2? 2/9. And let's do one more. 4 minus 1 is 3. What's 1/3 to the third power? 1/27 times 2? 2/27. All right. So now what we want to look at is the partial sums. If you add up the first term in that box, what do you get?
2.
Just 2. If you add up the first 2 terms in that box, you get 2 plus 2/3. Okay. And as a fraction, well, I'll just leave it as a decimal. 2.6 repeating. Let's add up the first 3 terms. 2 plus 2/3 plus 2/9. So take the answer that I just had before and add 2/9 to it. Add 2/9. We get 2.8 repeating. Now, add up the first 4 terms. So add 2/27 to the one we just had. So plus 2/27. What do you notice is happening to the number? 2.96. We'll call it 2.963. what does that look like partial sums are getting close to?
3.
They're getting very close to 3. So the idea would be if you had, well, actually, I can use real graph paper. Right? So if you had some graph paper like that, when you added up the first term, you got a 2. So think of that as like the first term added up to 2. The first 2 terms added up to 2.6. So 2.6. The first 3 terms added up to 2.8. 2.8. The first 4 terms added up to 2.9. 2.9. So the idea is if you keep doing these dots, they keep getting closer and closer and closer to 3, but they never would reach it. That's what I'm trying to explain from the previous page, from that page right there. Any question on that idea? Now, I can't connect them, right? I can't draw a curve through them because you can add up the first term and the second term, the third term, but can you add up 2.6 terms? No, there's nothing in between there. There's just nothing there. All right? So it's just like a series of dots that looks like it's getting closer and closer to that horizontal asymptote, which you guys said was at 3, and you're right. So now I did some more of these out. So S4, we did that one together, but I also did S5, 2.98, just to show you it's getting really, really close to 3. And then I did the first 6, 2.9959. Instead of adding them up manually, okay, like we did to do the first 4, this is using the formula we learned yesterday. Okay? Because to get to S6, I mean that takes a while. You got to add 6 things up that's all fractions. So it's easier to use the formula that we did in the homework. But the point is, you can see it's getting very, very close to 3, and it doesn't take long to get close to 3. Just by adding up the first 6, you're already at 2.99. So imagine by the time you get to like the first 20, it's going to be like 2.9999999. It's going to be extremely close to 3. So these type of problems converge or get very close to the number quick. They generally don't take a long time. All right. Actually, I already drew the picture, so we're not going to worry about that. All right, let's try this one. Let's see if we can find the sum if we add up every number from 1 to infinity for this one. Okay. You know what? Let me put k on top. So what we're going to do is we're just going to kind of try out the first maybe 4 terms and see if it looks like they're going to add up to something. What's the first k value that they want you to plug in here? 1. And then we're going to do 2, 3, and 4. If you plug in 1, what's 1 minus 1? 0. What's 3 to the 0? And 1 times 4? 4. Okay, so there's your first term. Second term, we're going to plug in 2. What's 2 minus 1? 1. 3 to the first power? 3. And what's 3 times 4? 12. Next one we're going to do is 3. What's 3 minus 1?
2.
3 squared?
9.
And 9 times 4? 36. And now let's do the fourth one. 4 minus 1? 3. 3 to the third power? 27. And now I need 27 times 4.
108.
That's going to be 108. So now, let's look at adding them all up. 4 plus 12 plus 36 plus 108. As I start to add those up, what does it look like it's getting close to?
Infinity.
Yeah, it's getting close to infinity. It's not like when I added up these, where we saw 2, 2.6, 2.8, 2.8. It was getting closer to something. This one isn't. Okay. These are approaching infinity. So when they ask you to find the sum here, it doesn't add up to anything. So there is no sum. And what we say here is this series is divergent. Okay. Convergent means that it's adding up to a number. Divergent means it is not. Okay, so there is no sum to that problem. And it is divergent. It would have been nice if we could have just figured that out right away, rather than having to make this table and start realizing what's happening. Okay, so that's what we want to look at. So if we go back, so this one, this is the one we did earlier, was convergent. This one was divergent. What's the difference? There's something you can look at right away.
One has a fraction.
Where?
In the parentheses.
Right. That's a number less than 1. That is a number more than 1. That number alone that I'm pointing to in each one, that will tell you if it's going to be convergent or divergent. I pretty much already said that to you. If you start adding the sums in this one, like if you were to put these on a graph, which I can't even do because it gets very, very high, you would not have a horizontal asymptote like in this one. The sums in that other problem would look more like, as you keep adding more terms, it just takes off and goes straight up. Okay. Yes?
So if it was 1, would it be, or would it have a vertical asymptote, or would it be like the last one where it's like infinite?
You mean if this was exactly a 1?
Exactly.
We'll see what happens in a second.
Okay.
Yeah. So when you're trying to add up a geometric series, sometimes it'll converge, sometimes it'll diverge, and it all depends on that number. So let's try different values for r and see what happens. Okay, so let's try it on the calculator. So this is the formula we learned yesterday. This is the formula for the sum of a geometric sequence. I'm going to try different values for r and see if I notice which ones are getting closer to a number and which ones are not. Okay. Let's try 0.8. Okay, so you need a few parentheses to type all this in. So it's going to be 1 minus 0.8 to the x. That's my numerator. Divided by 1 minus 0.8. Okay, let's look at the table. And the table is going to tell us what's going on. All right. If you add up the first, we should probably 1 minus 0.6. Okay. I want to make it so I can type in a value. Let's put on ask. So if you add up the first 5 terms in that sequence, if R is 0.8, you'd get 3.36. If you add up the first 20 terms in that sequence, if R is 0.8, you get 4.94. If you add up the first 50 terms in that sequence, if R is 0.8, you get 4.99999. If you add up the first 200 terms, you get, well, that's too many. The calculator ran out of decimals. But if you add up the first 100 terms, you get that number. So if R is 0.8, does it look like we're getting closer to a number or no? Yeah. So when R is 0.8, we do get closer and closer to a number. If R was 0.9, let's try that. Let's go to the table. Okay, so R is a little bit different number, so we're going to get a different answer. But look what happens. If we add up the first 200 terms and R is 0.9, we get that number. So this time, does it look like we're getting closer to a number? Or no? Yeah, we're still getting closer to a number. The difference is we're getting closer to a number a little bit slower. Okay? The closer that this starts to get to 1, like if I made it like 0.95, it would still get closer to a number, but it would take a little bit longer. But it's still going to get closer. Now let's try 1.1. So let's put in 1.1 and 1.1. Let's go to our table. And let's look at what happens now. If we add up the first 5 numbers in that pattern, if R is 1.1, we get 6.1. If we add up the first 20 numbers, we get about 57. The first 50 numbers adds up to 1,163. The first 100 numbers is over 137,000. So what's happening this time? Are we getting closer to a number or no? No. And the key difference between these two and those two is the R value. What values of R do you think you would get closer and closer to a number? Less than 1. And what values of R do you think would cause you to diverge and go away from a number? Above 1. Now, somebody asked, well, what if it's exactly 1? Well, think about what would happen there. If you plug in a 1 right there for R, what would you end up with in the bottom?
0.
You'd end up with dividing by 0. Can you divide by 0? No. So the answer is R will never be a 1. It can't be. It can be more than 1 or it can be less than 1, but it will not be exactly 1. Okay. So from kind of exploring what happens if you change the R value, we saw that if the absolute value of R is less than 1, okay, so think about what that means. How far away from 0 can you go on the positive side if you want to be within 1 unit? You can go up to what?
0.99.
You can also include the 1 unit. So you could go right up to 1. And how far away can you go from 0 on the left side if you still want to be within 1 unit?
-1.
You can go right up to -1. That is kind of the zone of R values where things will converge. R will converge anytime you have a number between -1 and 1. I didn't do a negative, but I could show you a negative. Like, let's do -0.5, and let's make this a -0.5. It'll still converge. So if you go to your table and look at what happens, it looks like it's getting very close to the fraction 2/3. So anytime that your R value is in that green zone, it'll converge. What do you think will happen if the R value is over here? That's going to diverge. What do you think will happen if the R value is over here? It'll also diverge. Okay, so that shows you when it'll converge and when it'll diverge. The green is converge. And what would it converge to? Okay, so once we know, all right, that problem's going to converge, how can we quickly figure out the answer? The answer is 4. But how can we get that without, I don't want to write it all down. I want a faster way to do it. That's the formula for what it converges to. It's actually a simpler formula than the one we learned yesterday. So adding up infinitely many things and figuring out what it adds up to is actually a simpler formula than adding up a finite amount of things. Okay, so let's go back to the problem we did by doing it by hand. And let's try that formula and see if we get the same answer a lot faster. So it's a sub 1 divided by 1 minus r. So here's what we got when we did it by hand. 2.96, 2.98, 2.99. What did it look like this was getting closer to? 3. Let's try our formula. A sub 1 divided by 1 minus r. Okay, so first you need the first term. What number do you plug in for k to get the first term? 1. Okay, what's 1 minus 1? 0. What's 1/3 to the 0?
1/3.
No, 1/3 to the 0 is 1. And then 1 times 2? 2. So the first term is 2. And what's the r value in that problem? 1/3. What's 1 minus 1/3? 2/3. Let's take 2 and divide by 2/3. Let's see what we get. 2 divided by 2/3. 3. That's exactly what these numbers are getting closer and closer to. So this formula will automatically tell you what you're getting closer to without having to figure that out by hand now. Now that formula only applies to something that's convergent. Could you use it on something that diverges? Like if R was in that red range that I showed you? You could, it just wouldn't have any meaning. Doesn't tell you anything. Okay, so it will only converge if it's in that green zone. That's the only area that that formula has any purpose. Don't use it in the red zone. Doesn't work. All right, so let's look at this one. So they want us to add up every number from 1 to infinity in that formula. Okay, so first of all, is this the type of problem that's going to converge, or is this problem going to diverge? Yeah, this is going to converge. How do you know it converges?
R is less than 1.
Right, the R value, which is right there, that's the R value. The R value is in the green zone. It's 1/2. It's right about there. Okay, so that's good. So it's going to converge. So R is 1/2. And if you plug in 1 for k, what is your first term? 5. Yeah, the first term is basically whatever's right there. Because when you plug in 1, 1/2 to the 0 power is 1, and 1 times 5 is 5. Okay, So let's see what this adds up to. Take the first term and divide by 1 minus r. Okay. What's 1 minus a half? That's a half. And what's 5 divided by a half?
10.
10, right? Not 5 divided by 2. That's different. 5 divided by a half is 10. Yep. So if you were to start writing all these numbers down and adding them up, just like we've done before, they would get very close to the number 10. It would be like 9.9 repeating. Question on that? Let's look at one more. Let's do k equals 1 to infinity of 3 times, let's say, 1/3. Let's not do 1/3. Let's do 1/4. Okay, that's fine. Okay, so is this one going to converge or diverge? It's going to converge. Yep. What is the first term, if you plug in 1 for k, in that sequence? Yep, first term is 3. And what is the r value? 1/4. So now fill it into your formula. A sub 1 over 1 minus r. So it's 3 divided by 1 minus a quarter. What's 1 minus a quarter?
3/4.
3/4. Okay, so let's see what that comes out to. 3 divided by 3/4. 4. Okay. So if you add up every number from 1 to infinity, it converges to 4. So 2 ways you can say it. You might see either way on the test or in the homework. So the sum converges to 4, or the limit of the sum is 4. Means the same thing. Converges, limit, it's just an idea of something you're getting close to, but you're not reaching. All right, let's write out a few terms, because I want to just look at one more thing with this, and then we'll be all done. So the first term is 3. We already did that. Let's plug in 2. What's 2 minus 1? 1. What's 1/4 to the first power? And what's 3 times 1/4? What is it? 3/4. Okay. Let's do one more. If k is, we did 1, we did 2, let's do 3. What's 3 minus 1? 2. What's 1/4 to the second power? 1/4 times 1/4. 1/16th, and then times 3. 3/16. And what would the next one be? 3 what? 340.
Would it be 64th?
Well, what's happening each time?
Multiplying by 4.
Yeah, you're multiplying by 4. So times 4, so times 4, 3/64. All right, so on the test, you can get 2 different questions about this. What are the individual terms converging to? What are the sum of the terms converging to? That's 2 different questions. So the individual terms are converging to, don't add them up, just look at what's happening to each term. What is the term getting closer and closer to? 0. The individual term itself is getting closer to 0, because the next one would be like 3 over 64 times 4 is 256. And then times, the next one would be 3 over 1024. So the individual terms are converging to 0. The sum of the terms is converging to 4. Any question on the difference between those two things? The individual terms versus the sum of the terms. So that's definitely important for the test. So that's 11.2 part 2. So that's the homework tonight. Let me also put a list of topics that are going to be on the test, and I should be able to get that up before you leave. So if you have any questions, you can let me know.